Well, there's not much more to this lesson. We're going to cover section 4.2, but not very much of it. And hopefully you have a calculator with you. I don't know if you're going to actually need it, but hopefully you'll have it with you anyway. We're going to go over a couple theorems. One that we've already gone over before. We covered this one while we were going over the last section, in which f is a polynomial function, and that's what we're talking about here. X minus c is a factor of f of x if and only if f of c is equal to 0. F of c. So that means that, let's say that f of x is equal to, I don't know, x minus 2 times x plus 4. By now you should see and you should understand that the two zeros of this function are 2 and negative 4. Remember, the zeros are where the graph of f of x crosses the x-axis, so they're x-intercepts, they're zeros, and they're also, they appear in the factors being subtracted from x. They are each in a factor, so x minus whatever that c is a factor if f of c is 0. So we know that to be true. If f of c is 0, then x minus c is a factor. And so I was just helping my daughter on her geometry tonight, and this is called these are two conditional statements. One would be the conditional statement, and the other is the converse of the conditional statement. So you guys got all that in geometry. And when both the conditional statement and the converse are true, it means that it's called a biconditional statement. I bet you all remember that anyway from geometry, so I didn't even need to tell you that. Okay, well, let's take a look. Number of real zeros. This is helpful when we're using our calculators and we don't really know where the graph is, but we want to find the number of zeros. And when we look at, let's say, let me label these. The lower left-hand corner here, we've got a second degree polynomial. So an n behavior model be y equals x squared. This one over here, this is a x to the first degree, so there's a first degree polynomial there. This one here is well, let's see. More of zeros. Yeah, so this one down here, I'm gonna call it a third degree polynomial. 1, 2, so, and then this guy here, 1, 2, 3. This is a fourth degree polynomial, and then same with this one up here, a fourth degree, and then this one over here, 1, 2, 3, 4, 5. This one's actually a sixth degree polynomial. So we talked about turning points, and the same thing with turning points, well, actually almost the same thing. So the number of real zeros can't be more than the degree of the polynomial. So in other words, if we have a second degree polynomial, you can't have more than 2 times. The graph of that function can't cross the x-axis more than 2 times. And with a first degree, so a linear function can't cross the x-axis more than once, and it goes on and on. So third degree polynomial, sometimes it does cross the same number of times as the degree, but other times, like this fourth degree polynomial, it only crosses twice and then doesn't cross anymore. You saw over here in the lower left again, the x squared didn't cross it at all. No x-intercepts, none. So again, at most, you'll have at most the same number of real zeros as the degree of the polynomial. And anyway, just wanted to illustrate that. So when you're looking for zeros, you don't have to look everywhere. Once you find the same number of zeros as the degree, then you are done, because there won't be any more. Okay, so it's a helpful theorem to remember, so you don't have to go searching everywhere for these real zeros. Okay, so let's take a look. There's one last theorem here. We're almost done. One last theorem that is very, very important, the intermediate value theorem. And that says that basically, it's kind of a common sense theorem, by the way. If A is less than B, so we have A over here, just to give you an idea, if you look at this graph, you've got A over on the left-hand side and B. That's how we normally label two random values of x along the x-axis. Okay, so from A to B, so A is less than B. And f of A is down here, and f of B is up there. As long as f of A, the value of the function, and f of b, the value of the function at b, have opposite signs. Okay, what does that mean? Well, it means that f of b, in this case, f of b would be positive. Okay, and down here we can see that the value of the function at a is negative. So the bottom line is, as long as f of a and f of b have opposite signs, there is at least one real zero of f between a and b. So to put it kind of in inputs and outputs, if the outputs have different signs, then there's going to be an x-intercept in between the inputs. Okay? And that's all that theorem says. So if you're looking on your calculator, I'm going to show you one example here. When you're looking on your calculator, if you know you have opposite signs, then well, you know that there's going to be a zero somewhere in between. Okay, so let's see how that works. Using the intermediate value theorem to locate a real zero. So a typical problem in this case would be show that this function has a zero between 1 and 2. Well, how would you show that? If you weren't able or allowed to use your calculator for this, how would you show that? Well, the only thing you can do on this one would be to figure out what is f of 1, and f of 1 is 1 to the 5th minus 1 cubed minus 1. So what is that? 1 minus 1, which is 0, minus 1. So f of 1 happens to be negative 1. Okay, so if we place a point on the graph, we know that f of 1 is right there. And let's figure out what f of 2 is. F of 2 is 2 to the 5th minus 2 cubed minus 1. 2 to the 5th is 32. 2 to the 3rd is 8. 32 minus 8 is 24. 24 minus 1 is 23. So way up here somewhere, okay, way up here, I can't do that. Sorry, the iPad is acting up. So we can see that when x is equal to 2, the y value is way up here in the first quadrant. When x is equal to 1, the y value is down here in the fourth quadrant. Okay, so if we were to connect the graph with a curved line, we're not really sure what it looks like at that point. But all we know is that there's going to be an x-intercept, somewhere in between 1 and 2. So somewhere on this interval, right in here, there's going to be an x-intercept. And sure enough, there is an x-intercept because the graph will have to go from down here to up here. It's kind of like this. Here's Edison, and let's say up here is let's say Estancia High School, and right behind Estancia you have the Sheep Hills. I don't know if you guys call them Sheep Hills. That's all I've ever heard of them, as called Sheep Hills. But anyway, to get from Edison to Sheep Hills, you've got to be able to cross, or you have to cross if you're walking. You got to cross the river trail. Okay, you got to cross the river trail. There's no way you can get there without crossing the river trail. So there you go. Okay, and then that's really it. That's really it. So what I'd like you to do is do these, what is that, 8 problems? So you have 8 problems. I also, for those of you that don't have your books yet, or if you don't have your books at home even, you can go ahead and click on the link on Canvas, and that'll take you to this to these 2 pages, and then also the third link for the answers to the odd numbered problems. And then just bring all the work to next class, and I'll see you then.